Hey folks, Todd Coburn with the Aerospace Structures series. This is the first video of our Dynamics playlist, and in this video we're going to cover some of the fundamental concepts that underlie what we're going to do in this class. This material is very similar, basically identical to what we lay as the groundwork for our statics class as well, but it's so critical to understanding the other concepts that most books recover this same material. So stay tuned, and if you have a strong grip on your statics, you maybe can fast forward, but this may help set the basis of where what we're going to do in dynamics feeds into what we're going to do. What we did in statics feeds into dynamics. Two books that I use for developing most of my content are Beer and Johnson's Dynamics book and Merriam and Crage's. Our classes at Cal Poly Pomona use Merriam and Crage. It tends to have fewer tricky problems. Beer and Johnson has a lot of tricky problems. Both are great books. A lot of the slides that I'm going to use at various points in both classes will be from Beer and Johnson, and they'll be looks at both Beer and Johnson and Merriam and Crage slides that correspond with their books. So if you're using either of those books, you're in good setting. There are other great books out there as well, and the same basic concepts will apply. So first, it's useful to think about what we're talking about here. This word mechanics, while we tend to think of the person who's working on our car, the word mechanics describes a subject, and there's the Greek word mechanika. We're going to be studying the relationships of force, matter, and motion. Forces, that's when something's pressing on something. That's called force. Matter, that's objects that have mass and therefore weight when you have mass with forces being applied, accelerations, and motion. Force, matter, and motion. These are the three basic ideas we're going to look at. We could say that mechanics describes the conditions of rest and motion for bodies under the action of forces. If there are no forces, you typically won't have changes in rest or motion, but if there are forces applied, that's when we get changes. That's what we're going to be studying. Okay? And the foundations of this go back, they're old. We go back to 287 for Archimedes, 380 something for Aristotle. Galileo comes along in the 1500s, and Kepler, Newton later in the 1600s, and others have built on these principles. So these are old concepts. What we're going to do with them isn't that new, but we're going to build and build and build until, and we're going to keep it simple, and we're going to find that we can solve some of the mysteries of the universe with some of these simple ideas that have been laid out by some amazing thinkers that came before us. Okay, we're going to be looking at some concepts like rigid bodies, deformable bodies, and fluids. Okay, and this is kind of getting increasingly difficult. A rigid body is one where, whether it's rigid or not, we're going to treat it as if it doesn't deform under the action of the forces or when it's moving. It basically does not deform. A deformable body, we're going to try and account for some of those deformations, and fluids are moving all over the place, like herding cats, even worse. Okay? With under rigid bodies, once we say okay, the things we're talking about, when we say rigid bodies, we're talking about metals or any kind of material, soils even. We're going to be talking about bodies at rest and bodies in motion. So in statics, we focused on bodies at rest. And even if we were talking about bodies in motion, we pretended they were in rest. We imposed dynamic equilibrium in the sense that we treated everything as a static load force, and that enabled us to solve a lot of problems quite simply. Okay, with dynamics, we're going to be accounting for that motion, and that's actually a major key for solving problems when things are moving. Okay, deformable bodies, with deformable bodies, we're going to start dealing with deflections. We're going to see some of that in our Strength 1 and Strength 2 classes. And yet we're generally going to assume that the deformations are so small they don't affect the equations of equilibrium and motion. Why? Mostly because it's negligible, but also because it just gets really hard, and it's difficult to get correct solutions because of some of the complexities. And then fluids, which is also harder, and we'll deal with that in a completely separate class, where we're typically going to assume that they're incompressible, and but there's also compressible fluid dynamics as well. Okay, we're not going to deal with it. What we're going to focus on in this class, we already covered statics in our statics playlist. Now we're going to be talking about dynamics. Got it? All right. So we're going to deal with the same basic concepts that we dealt with in statics. Space, where we're going to locate something in one dimension, two-dimensional space, or three-dimensional space. We're going to be dealing with time, because at one time something might be there, at another time it might be somewhere else, and that defines the motion of it. So we're going to need to account for that. Mass, which is like a lumpiness thing about a material. Now we're a little more used to dealing with forces in the United States, or weights. And a weight is just a mass that has gravity acting on it. So mass is this immutable property that we possess, that when an acceleration occurs upon, or it acts upon us, that causes a force, which we call weight when it's from a gravitational one. So we're going to have, also we can think of mass as the resistance to change. You may know some folks that are very resistant to change. You can tell them, hey, look, we're going the wrong way, and they just don't get it. They're very resistant to change. No matter what you say, they aren't going to sway whether they're right or wrong. You may know other people who, if you tell them, ooh, there's a monster in the closet, they're going to run out of the house screaming. They flit about like on the wind, like leaves on the wind. They're so afraid of everything, and they just jump around. So that would be somebody with low mass, if in this analogy, versus somebody with a lot of mass. The more mass, the more resistance to change. In football, we see this. Big old linemen. The linemen tend to be large because they're harder to move. You get a real big guy, especially if he's strong on the line, and just his mass alone makes it very difficult to get through in. So the more mass, the more resistance to change. Okay? This is why a lot of times the quickest football players are the smaller guys, because it's easier for them to move. They have less mass. There's less resistance to change. It takes less strength and agility to move something that's very light rather than something that's very heavy. So structures are people too. The more mass they have, the more resistant to change. You can apply a force to something, and if it has more mass, it's going to respond much less impetus than something that has less mass. We're going to deal with, mostly we're going to deal with translational forces. We have forces applied, we're going to deal with what happens, but we also are going to kind of start tagging into gravitational forces. It can get complicated. We're going to keep it simple for this class, and we're going to have later classes where you'll learn more about some of the complexities with gravitational forces, but we're going to lay the groundwork in this class. Remember, force we learned in statics, it's the action of one body on another. They are characterized by a point of application, a magnitude and a direction. A lot of time we say just magnitude and direction, but it's not only magnitude and direction, because where it's applied can affect the overall what happens to the body. Okay, so point of application, magnitude and direction. A force acting here, like for example, if you apply a force at your center of mass, you're going to tend to have a translation. If you apply it off of your center of mass, you're going to have a translation, but also a rotation. And this is where the point of application matters with forces. We're going to deal with these as vectors, just like we did back in statics. And we're going to talk about particles, where we can assume that a particle is some tiny amount of matter in a tiny little point in space. And we're going to talk about rigid bodies, which is a combination of a bunch of particles, but they have fixed positions. So if you think, wait a minute, let's say you have a little tiny little ball and a huge ball. You could say the little ball is a particle and the big ball is a rigid body. Really, you could deal with both of these as a particle. We're going to study that a little further in a minute. But if you just imagine that this big ball is a bunch of little balls all kind of attached together, and they have fixed positions relative to each other, which means the relative positions don't move, that's what we're going to define as a rigid body, because we can actually treat groups of particles as rigid bodies if they keep that relationship between each other. Okay, so a lot of this is getting into some extra complexity, but we're going to keep it simple. We're going to deal with particles first, when we can just ignore the size of the thing and just talk about its mass as like a tiny little point in space, and that if it has larger than that, that doesn't really affect its motion. That can keep the equations a lot simpler. We can do some really cool things. Later, we'll deal with what we call rigid bodies, where we're accounting for some of that size not being all at one point. And the main deal there, the main idea we're going to explore in this class, is that if you have something that's larger, and if you apply a force at the center of mass, it has a translation. If it's off the center of mass, it's going to have a translation and a rotation. And that's the piece we're going to capture in this class. And then there's more we can do later in more advanced studies. Okay? So let's just have a little quiz here. Would you call this a particle or a rigid body? It kind of depends on perspective, right? If we look at that and it's the size of a grain of sand, we're going to think of it as a particle. If it's the size of a house, we're going to think of it as a rigid body. A little ant is going to have a different perspective on that than a person, if it's that size. This obviously looks like a rigid body because it has more size, and we can kind of see this going to be pivoting about this point. This is going to need to be treated as a rigid body. We can assume so many forces acting on that first little point that it just takes off in a translation, and the size of it doesn't matter. It's like a little tiny point. But this other part, you can see, depending on where you apply your force, it's going to have a different response. That needs to be treated like a rigid body. These particles, if they don't have fixed positions relative to each other, they each need to be accounted for as a particle, separate particle. This little bug, once again, if we're looking from a larger perspective, that's just a particle. We can deal with a lot of things. But if you get down close, if you're like a little flea on the bug, then all of a sudden you need to treat it as a rigid body. This car actually is a rigid body with a lot of moving parts, but a lot of we can do a lot of things with that, studying them in this class, where we can look at what its acceleration is, what its position is, and these things based on the forces that are applied to it. So we're going to be learning to hone our judgment in determining whether something can be treated as a particle or rigid body. In fact, a lot of times we'll start by analyzing something as a particle, even if it's really not, and then move on into a rigid body assumption, even if it's really not, and then move on into more complicated techniques. And this can allow us to kind of say, okay, we got a rough answer here, and now we got a little better answer, and then we got a little better answer, or our answer now we don't even understand it, so we'll go back to the simpler idealization. Okay, we're going to be studying some of these ideas. Rocket, once again, can be treated as a rigid body, or for many kinds of analysis as a particle. So we'll be studying that out. Okay, we're going to be talking about Newtonian versus relativistic kind of mechanics. With Newtonian mechanics, or for following the mechanics that Newton kind of perfected a little more, we're going to be talking about space and time and mass as if they're independent of each other. Space is there, and there's time, and there's mass, and they don't really change each other. And force, where force in this system is related to mass and change in velocity. Remember, the force is equal to the mass times the acceleration, or another way to say that, it's the mass times the change in velocity. We're going to be studying these concepts in this class. With relativistic mechanics, time can vary with position and mass can vary with velocity. And in these cases, things get really hard. And even when we're doing this, we usually start with a Newtonian system because it's easier. And then as we get on into higher studies, we can start trying to account for more accurate solutions by accounting for things like relativistic mechanics. Okay? So that is our first building block. It's one piece of our first lecture. Be sure to watch all the lectures for lecture 1 so that you get the whole picture. I decided to keep these small so you can focus on one piece at a time. We're going to build all these pieces for lecture 1, and then we're going to start jumping into some of the higher where we start applying some of these principles and expanding upon them. And it'll be fun, and you can learn to do some really cool things. Stay tuned.